A double layer capacitor in practice in a discharged state looks something like this on the left side here. Note please that I neglected any kind of solvent molecules here simply for clarity. In the discharged state, we do have our two electrodes on the left and the right side. We do have our electrolyte, which is shown in light blue here. We have a separator in the middle, which allows ions to pass through it, but make sure that our electrodes never would touch each other. And if we're in a discharged state, we basically have a random ion distribution in there. So we have a bulk situation, there's no preferential attraction to one or the other electrode, and our ions are just randomly distributed in our electrolyte. Now, if we charge our double layer capacitor, you get into a situation like this. Let's say we apply a positive charge to the electrode on the left and a negative charge to the electrode on the right. You will have the anions, so the negative ions, moving to the left, and our positive ions, our cations, they will move to the right side, to the negative electrode. And by this, you're again creating this situation where you have a high concentration of negative charges close to the electrode, and it gets lower and lower until in the middle you reach something like a bulk state where there's roughly equal amounts of both ions. And once you approach the other electrode, you will again find more and more positive charges on this side. And this charge separation in this case is what again allows you to store energy in this so-called double layer capacitor. The contribution we will look on now. So pseudocapacitance originates when so-called specifically adsorbed ions out of the electrolyte permeate this double layer at which we just looked. And don't worry, we'll in a second have a look what these specifically adsorbed ions are. So by this, we are able to store electrical energy by means of so-called reversible Faradaic redox reactions. So now we actually do have something like a reaction which is, to be very strict, not a purely electrical storage anymore, but supercapacitors are regarded as electrical storage device. So here we have an electron charge transfer between the electrode and a desolvated and adsorbed ion. And we can only transfer one electron per charge unit. And this is a process happening in a very fast sequence of reversible redox, intercalation, and electrosorption processes. So to be very strict, again, this is not really a chemical reaction. It is some kind of electron transfer, but we are not really regarding this as a chemical reaction. And this is why it is part of this chapter here. So this distinction is made because we're actually not forming chemical bonds. You can imagine this as any kind of molecule going to the surface and just temporarily giving a part of its charge to the electrode. And this happens in a very fast sequence. So Faradaic pseudocapacitance is usually limited by the finite quantity of reagent and also of the available surface area. So the capacitance which you can yield from pseudocapacitance depends on the nature and the structure of the electrode itself. So how does this look now in practice? And this might seem a bit counterintuitive at first, but going from a capacitor to a supercapacitor, the only thing which is different is that you have this so-called specifically adsorbed ions. These are the main contribution to pseudocapacitance. And this is actually negatively charged ions adsorbed onto this negatively charged surface. Even though if it might seem intuitive that it actually should repel each other, this is exactly where the fact comes in what I told you before, that you can have a very fast and temporary electron transfer to this negatively charged electrode, and this helps it to stay here on the surface. And this is what makes a capacitor basically a supercapacitor. Although it is noticeable right away that, of course, these places here very close are at the electrode with no solvent molecules between the electrode and the ion is very limited simply by the surface area which the electrode provides. Now, supercapacitors, to sum it up, we would expect a theoretical capacitance of a double layer to be 355 microfarad per square centimeter. It's not so important now what this absolute value is. I just want to give you the contrast here that the real value you can actually obtain is only 5 to 50 microfarad per square centimeter. So you have a value which is significantly less than what you would theoretically expect. And this is due to the alignment of water dipoles, that this is affected and in fact actually compromised in a way. And you see that the relative permittivity of water cannot be assumed to be around 80 as we saw before, but we would rather have to assume a value somewhere between 3 and between 6 and 30. Also, the overall capacitance has multiple components. And please notice that if we regard the inner Helmholtz plane and the outer Helmholtz plane as separate components, they have to be seen as components which are connected in series. And the rule for electronics when you connect a capacitance in series is actually that the total capacitance can be calculated by 1 over the total capacitance equals 1 over the capacitance from the component 1, in this case from the inner Helmholtz plane, plus 1 over the capacitance of the outer Helmholtz plane, which is C2 here. So the total capacitance is lower than the capacitances of the individual contributions just added up. So what we can do, however, to increase the pseudocapacitance even further is we can exploit the dependence on the individual capacitance from the area. So we do know that still for each of these components, for the inner Helmholtz plane, for the outer Helmholtz plane, and also for pseudocapacitance, the capacitance is directly proportional to the area of the electrode. So by maximizing the area of the electrode, we can maximize the capacitance. And this is why as electrodes, as these materials, we often choose porous or very rough electrodes which have favorable adsorption properties. So ions would like to go to their surface, and therefore we will have a high pseudocapacitance. A typical example for this, just to get an idea about the size scales of this, is, for example, activated carbon. If you think about a plate of metal which is 1 meter to 1 meter, it is pretty obvious that you will have a surface area of 1 square meter, or 1 foot to 1 foot is 1 square foot. Okay, but if we have a look at this activated carbon, we usually determine the surface area by a value given as the specific surface area, giving us a surface area per gram of material. And for activated carbon, this value is 500 up to around 3,000 square meters per gram. And just as a comparison, a soccer field is 7,140 square meters. So we do have activated carbon, we do have a material where 1 gram can have up to around 40 to 45% the size of a soccer field. And this is some very huge surface area, which of course helps pseudocapacitance to deliver at least a notable contribution to the overall capacitance.